Hey guys, in your presentation that you guys did last week, you had three different gas laws. You had Boyle, you had Charles, and you had Gay-Lussac's law. With those three gas laws, they help to explain the behavior of gases in the real world. I've got three different demonstrations to show you just so you can see a real live version of what you actually did. A lot of people just looked for pictures instead of looking at videos, so maybe this will help you to figure out what is going on with Boyle's law first and then Charles and Gay-Lussac. So for the first law that you have for Boyle's law, he found out that it was an inverse relationship. That means that if one variable goes up, the other one goes down. So I made this little PTV card. I wrote out the letters PTV, and it needs to be in that order. And with your PTV, P is pressure, T is temperature, V is volume. For Boyle's law, it's looking at pressure versus volume, so you're going to hold temperature constant. And when you hold temperature constant, that's where you actually hold the card. Had we been in class, you would have made one of these yourself. So if I hold it on the T, when my pressure goes up towards the ceiling, the volume goes down to the floor. Same thing here, if my volume increases, my pressure is going to decrease. So when you have an inverse relationship, if one goes up, the other one goes down. To show you this, I have a water bottle here. In the water bottle, it has a ketchup packet that I actually got from a neighbor the other day on our neighborhood page, since we can't go anywhere right now. So right now, the ketchup packet is actually in the water floating. I don't know if I can make it float any more than that, but you can see it's actually floating in water. The reason why it's floating in water right now is its density is less than the water. There's actually a little air bubble inside of the ketchup packet itself. That air bubble is what we're going to deal with first. So with the water that I have in here versus my ketchup packet, we're actually going to look at the little pocket of gas that's inside of the ketchup bottle, or ketchup packet, sorry. So what I'm going to do is I'm going to squeeze the bottle. When I squeeze the bottle, it's going to increase the pressure inside of the container. When I increase the pressure, the volume of that air bubble should go down because it's an inverse relationship. Pressure's going up, so my volume's going to go down. So if I squeeze this, the ketchup packet actually goes to the bottom. And then when I let go, my pressure is going to decrease, so the volume of gas goes back up. You can do this over and over and over. I can actually kind of get it to suspend in the middle. And what I'm doing is I'm changing the density of the ketchup packet itself. So as the volume of gas goes down, it changes the density, it goes to the bottom. So this one shows Boyle's law, where if my pressure increases, the volume of gas decreases, it gets smaller. When the pressure decreases, the volume of gas gets bigger again, and so that's what allows it to go back up. All right, the second gas law that we have is Charles' law. Charles' law actually holds pressure constant. So Boyle's law holds temperature constant. Charles is going to hold pressure constants. This is a direct relationship, just like the next one that you're going to see as well. For your direct relationship, if your temperature increases, so does your volume. Or if your temperature decreases, so does the volume of gas. So with the demonstration that I have for this one, I actually have a bar of ivory soap that I, again, borrowed from a neighbor. They were very helpful for me. And the bar of ivory soap, it's the soap that floats, is the thing that they have for in the commercials and things like that when we were little. So for your ivory soap, I'm actually just going to put this into a bowl and put it in the microwave. And when I put it into the microwave, it's going to go round and round, and I'm actually going to break for a second. I'm going to come back to the video. Okay, so the microwave just went off. It's been a minute, and I'm going to flip this around real quick. No, I'm not. I'm not going to flip it around. So this is now the soap. So what actually happened here, this soap started off just a regular bar of soap, and the soap actually has little pockets of gas inside of it. And with the little pockets of gas that it has inside of it, as the temperature increased in the microwave, sorry, let me get this. So as the temperature increased, the volume of the gas increased as well. And so that's what makes this kind of like a cloud almost. It's really light and fluffy. But with the soap here, you can actually do this. It has to be Ivory brand soap, but you can do this in your microwave yourself. Just make sure that you put it into a bowl, and then you can play with it. It's really fun. But again, it does have to be that Ivory brand soap. So for the last gas law that you actually had Gay-Lussac's law. Gay-Lussac's law holds volume constant. This is another direct relationship, just like Charles' law. When you hold the volume constant of a gas, if the temperature increases, so does the pressure. Or if the temperature decreases, so does the pressure. So the direct relationship, either they both go up or they both go down. For this demonstration, probably not very safely, but this is the best way that I had to heat it up. I've got a can. It has a little bit of water in there, and it's actually on, if you could tell, on the stove. And so as the water heated up, we now have a temperature. You see the steam, or hopefully you see the steam coming out of it. But the water that's inside of there is currently boiling. And I have a bowl of water here that has some ice in it. So I'm actually going to take this and I'm going to flip it. And when I flip it upside down, I'm going to take it off of the heat. We're going to put it into the cold. And the can actually implodes. So what actually happened there is that rapid temperature went down, and with that rapid temperature decrease, you actually had a rapid change in the pressure of the gas, and that caused it to actually move in.